I just want to say a little bit more about what we were talking about previously. One of the main driving forces for a lot of processes in physical geography is this idea of shear stress. And I explained previously that we have normal stresses where a force is being applied perpendicular to a surface, shear stresses where they're being applied horizontal or parallel to a surface. And I said previously that we can calculate the shear stress in different situations if we know the components that contribute to shear stress. So for example, underneath a theoretical ice sheet, so here's our ice sheet surface, here's the ice, and here's the glacier bed. Sliding at the glacier bed is driven by the horizontal component, the shear component of the stress being applied to ice at that location. Internal deformation within the ice, the creep of ice, that's driven by shear stress being applied at each level through the thickness of the glacier. So if we could calculate what that shear stress is going to be, then we'd be able to predict and understand the amount of motion that we're generating. And we can do that using a couple of very simple equations that I mentioned previously. The first one is the shear stress equation, where tau is the shear stress that we're trying to calculate. Rho gh, well, that's essentially the weight of the glacier, the overburden pressure at a particular point, because rho is the density of ice, g is the force of gravity, and h is the thickness or height of ice at a particular point. So rho gh is basically the weight of the ice bearing down on whichever point you're interested in, or bearing down on the glacier bed. Alpha, well, alpha is that surface gradient. And the sign of alpha simply converts that number from being somewhere between 0 and 90 to being a number somewhere between 0 and 1. 0 if it's horizontal, 1 or 100% if we have a vertical slope, which kind of simplifies the maths for us. So basically the shear stress is given by the weight of the ice and the surface gradient. Now, if we're interested in, as I drew previously, this column of ice here all the way down to the bed and calculating the amount of deformation that we get within the ice at each layer, or the amount of force driving sliding at the glacier bed, well then alpha is a constant all the way down this column. It doesn't change because we're always underneath that same driving surface gradient. Rho, the density of ice, and g, the force of gravity, that doesn't change either. So the only thing that actually changes is h, the thickness of ice bearing down on that point, or that point, or that point, or all the way down to the glacier bed. So to calculate the shear stress at the glacier bed, we'd simply need to know the gradient of the ice surface and the thickness of ice bearing down at that point. But how do we then calculate the amount of motion? So for example, if we're trying to calculate how much strain or deformation is going to be occurring in the ice here, how do we do that? Well, for that there's a second equation. I always joke with the third year glacier students, there are only really two equations that you need to become an ice sheet modeller. And here's the second one. E equals a times tau to the n. Now that's often referred to, well, that is Glenn's flow law, named after the glaciologist John Glenn who came up with it. And E here, well, that is the amount of strain or deformation occurring within the ice at a point. That's what we're trying to calculate. How much creep deformation would there be? And he says, well, it's a function of tau, the shear stress that we've just calculated here, so we can calculate shear stress and stick it into this equation. But it isn't simply that the amount of strain is equal to the amount of stress. The amount of strain is equal to the amount of stress raised to a power. There's an exponent there. Typically, people use a number 3 there. So the strain is equal to a times the cube of the stress. So if you double the stress, you increase the strain 2 times 2 times 2, much more. So you get a very significant increase in strain for a very small increase in stress. And A here, that's just a term that we throw in to represent the hardness of the ice, because ice can be harder or softer depending on the temperature. Warm ice is softer, so you throw in a bigger number here to say that you get more strain for any amount of stress, whereas if the ice is cold, you'd throw in a low number here to indicate that you're getting a lower multiplier for the amount of strain that you're getting from the amount of stress. Now, at first glance that seems very complicated and messy, but just pull it back to the very basics. All we've really got in there is we've said, Well, to calculate the deformation, the creep, the movement within the ice at different levels through an ice sheet, all you need to know is the surface gradient there and the thickness of ice or the weight of ice bearing down on the point that you're interested in. So tau is given by rho gh sine alpha, and then you can calculate E, the strain or the deformation, because the strain is a function of the stress, making allowance for hardness or temperature. So it's a very straightforward kind of relationship. Now in the other video that this is associated with, you'll have seen how there's a very similar approach that you could take looking at mass movements or landslides, and you can predict whether or not there'll be sufficient stress to overcome a particular amount of strain, to overcome a certain amount of resistance and generate the strain, using a very similar approach based on shear stress and the strength or the resistance, essentially that term in there, the resistance in the ice or the resistance in the surface material on the hill slope. So a final key point to take away from this is that relationship. There's an applied stress. There's always a resistance to that, whether there's friction at the glacier bed or cohesion or strength within the ice that we're trying to deform, so we'll call that strength or resistance. And then if the stress is greater than the strength, so if the force is greater than the resistance, then we get strain, or let's just call it movement. However, if the strength is greater than the stress, if there isn't sufficient stress to overcome the strength or resistance in the system, then we won't get that strain or movement. And that's just another of these big ideas to take away and think, well, okay, whatever we're looking at in physical geography, glaciers, landslides, rivers, whatever it might be, this is a basic relationship that applies in lots of different situations.